We're going to talk about this concept of percentiles. So I mentioned that in the last lesson, when we have something that's normally distributed, like SAT scores, when you get that grade report back, a lot of times it will say that something's in a certain percentile. And we're going to learn today what that actually means in relationship to what we know about z-scores. So here's a quick question. Kevin's math grade is steadily improving. His test average is now an 88, but the mean for all students is a 91 with a standard deviation of 3. So calculate Kevin's z-score. Same idea from yesterday. Observed minus the mean over the standard deviation would give you a z-score of -1. So part B, I kind of think it's a silly question. It says, does the z-score mean that Kevin did better or worse than the average math student? So I'm hoping that you can, if I didn't give you any more context up here, that a negative z-score on a test would mean that you are below average, right? So I think we already knew that, though, based on the scores that were given. So I said, well, worse since z is negative. But I think we already knew that. I guess the implication would be that if I didn't know anything about the actual scores, I just knew z was negative. In a testing sense, that means that you scored below what the average was for that particular assessment. Okay, moving on. On the normal curve below, we're going to label the mean and standard deviations of the class scores and put a star on Kevin's score. So here's what a really nice bell-shaped normal distribution looks like. And we're going to talk about what all those percents mean in just a moment here. So what you need to do is when the z-score is 0, what that implies is that that is the score that represents the mean. For the set of data, that was a 91. So if I go 1 below the mean, we know that a z-score of -1 corresponded with a test score of 88, which makes sense because the standard deviation is 3. So if I subtract 1 full standard deviation this way from the mean, that test score would be an 88. If I go this way and add a standard deviation, 1 standard deviation above the mean would be a 94. If I keep going in the positive direction, we get 97 and 100. If you wanted to, you could fill in those half values, right? You would just cut the standard deviation of 3 in half and add that on. If I go backwards, I'm going to subtract 3 and get that this score at 2 below is 85. And at 3 below, we've got an 82. Okay, so it's set to kind of highlight and indicate where Kevin's score is. Kevin's score, like we said, is right here. Okay, and at an 88. So we already knew that he was 1 standard deviation below the mean. The question is, well, what percentage of students are doing better than Kevin? Kevin is improving here, but based on where he falls in this curve, we can see all the percentages that would exist of student scores after an 88. So basically what you're going to do is you're going to probably just have to add all of those up. Other ways of doing it, maybe you can think of it already, but you'll notice because of the symmetry, we have 2 sections in the middle that are 19.1%, 2 sections here that are both 15%. So you can kind of shortcut this a little bit and say it's 2 times 19.1 plus 2 times 15. And then if I just add going all the way to the end of this tail here, plus 9.2, 4.4, 1.7, 0.5, and at the very end, 0.1. If I add all of that up on the calculator, you can trust me on this one or double check it, but that should be 84.1% of the students scored better than Kevin on this particular test. So then the next part is, well, what was on the other side? Kevin is doing better than what percentage of students? So who falls below Kevin? So you can do one of 2 things. If you want to know who's got a score less than Kevin, you can add up all these percents, but all the percents underneath this normal curve have to add up to 100%. So you could also simply calculate 100% minus the 84.1% to get a total of 15.9%. So what this means, to shade the area to the left to show that percentage there, okay? And the sum of that shaded area winds up being what we call Kevin's percentile. So Kevin's percentile is that he falls into the 15.9th percentile, which is just about the 16th percentile here, right? So what that means is that Kevin only scored better than approximately 16% of the students taking this test. If we think about other percentiles here, if you were average, right at the mean at 91, it's a 50-50 split on either side. So if you ever get a score report on something and it says you're in the 50th percentile, then you are average. Anything above 50%, you're above average. And again, that sometimes is a good thing, sometimes it could be a bad thing. Depends what context we're looking at. So now we're going to relate this idea of these percents under the normal curve to calculating what's called a percentile. All right, if we turn the page here, percentile is defined as the area under the curve to the left of the value. So we calculate that value of everything what was to the right of Kevin's score. That was not his percentile. It was everything before we got to his score at that standard deviation. So we know that Kevin scored better than or the same as about 16% of his class. I keep talking about SATs because that is a test that has a normal distribution of scores. So it says you took the SATs, you did not receive your numeric score for the math portion. The test service only stated that you scored in the 97.7th percentile. We know the mean score is 525 with a standard deviation of 100. Find your test score. I don't think this is very likely that they wouldn't report your test score for whatever reason, but if you score in the 97.7th percentile, I'm hoping you're thinking like, darn, I did pretty good there. Because that means you scored better than or equal to just about 98% of the students taking that exam. Okay, so what we can do is we can come about this in two different ways. Looking at the normal curve here, we know that the mean from the set of data is 525. So that would have to go right in the middle. And I know if I'm in the 97.7th percentile, that means that if I add up all the percents going from the left, I would have to stop when I got to a total of 97.7. Well, there's a few ways to shortcut that. You could either start in the middle because we know we've covered up to 50% there and just keep adding on. Or why not start on the right and start at 100% and just subtract till you go backwards to 97.7. That's probably the easiest method. And what you'll find is that the 97.7th percentile, which sometimes I'll write as that, percent ILE for percentile, corresponds with a z-score of 2. So if we know the z-score is 2, now it becomes one of those problems that we saw in the notes yesterday. So given a z-score, given the mean and standard deviation, can we calculate the actual score? So in this scenario, the z-score of 2 would equal the observed, which that's what I'm looking for, minus the mean of 525 over the standard deviation of 100. Okay, so go ahead and multiply both sides by 100 to get 200 equals x minus 525. And if you add that over, your score should be a 725. Okay, that is one way to do it. Now, another quick way to do this would be, since we know how many standard deviations from the mean that percentile corresponds with, you can just add on the standard deviation twice to get to that score. And maybe I'll convince you that that's a little bit faster. Since the standard deviation is 100, you really would just be adding on 200 to get a total of 725 there. So either or makes sense in this context. Will we always have the ability to do it that way? Maybe not necessarily. But in this scenario, it definitely works. Okay, so either of these solutions would work here. Okay, moving on to this question. Your friend accidentally fell asleep. Oh no. And what happened was, if you fall asleep, it's probably likely that you're going to be in the 6.7th percentile. Sorry for the crying kids in the background. It's bedtime at the All House. Okay. What score did she get? Okay, sorry to your friend here, but two different ways to do it. You can figure out what z scores in the 6.7th percentile. So that would just be going back up to the chart up here, adding up until you get to 6.7. Corresponds with negative 1.5. Okay, set up your equation and solve for x. Okay, z-score is what I know. Don't know the actual score, but we know the mean and standard deviation. So your friend scored a 375, not so hot on the math section. Okay, or on the other hand, we can subtract 1.5 standard deviations from the mean. Since the standard deviation is 100, that's going to be minus 150 for a total of 375. Okay, so a couple different techniques there that would allow us to figure out if you're in a certain percentile, what your actual test score is. Hopefully this idea of percentiles is starting to make some sense here. Okay, moving on to the next page. I'm hoping that you're sort of coming to the conclusion, well, what if your score does not fall on a whole or half number standard deviation from the mean, right? I mean, in the grand scheme of things, you're probably not going to score it exactly 2 above the mean or 1.5 below the mean. So we're going to wind up using z-scores and the graphing calculator to do some calculations in this scenario. So example 3, the top swimmer at FHS, and I know I have a lot of swimmers out there, swims the 50-meter backstroke on average in 39.7 seconds with a standard deviation of 2.3 seconds. I have no idea if that's fast or accurate, but if you're a swimmer, get back to me and let me know. Find the probability that she swims her next race between 37 and 44 seconds. Okay, sketch your normal curve with the mean at the center. Place 37 and 44 on the graph and shade the area that we're trying to find. Okay, so in a lot of these questions that involve z-scores and the normal curve, what we're going to do, we're going to make a big bell-shaped curve, draw a line underneath it that we can define some values with. And in this scenario, let me turn on the light, see if that helps a little bit. Yeah, that's better. Okay, in this particular scenario, we know that the mean is 39.7, so we can put that right in the middle. And what we're trying to figure out is what percent of swimmers would have swam the race between 37 and 44 seconds. So 37 is a little bit closer to 39.7 than, let's say, a time of 44 would be. So I'll try and make it look a little bit accurate, although as long as they're on the correct respective sides there, it's not a big deal. What you're going to do is you're going to trace up to the curve. And what we're looking for, the shading part, is we're looking for this area underneath the curve. And like we said, we can't necessarily use the chart that we were just looking at because these values don't fall at nice, that's my air quotes there, nice standard deviations from the mean. Okay, if they did, I can certainly go back to that chart. So what do we have to do? We have to calculate what are the z-scores that correspond with each one of those times. Okay, so in this case, a z-score for the time of 37 seconds would be negative 1.174, makes sense because it's below the mean. And a z-score for the 44 seconds is 1.870. Okay, so what we're going to do is we're going to take those z-scores, and since we don't know exactly where they fall on the chart, now's where we get to use the calculator to help us determine what percent falls underneath that part right there. Okay, so you have your graphing calculator. What we're going to do is we're going to type in the lower and upper bounds from our chart that we made up above. So the lower bound was 37 seconds. The upper bound was 44 seconds. The mean and standard deviation are the symbols that we have here. So the mean, this is actually the Greek letter mu, mu. In this set of data was 39.7. And the standard deviation for this set of data wound up being 2.3. That's the Greek letter sigma, by the way. It's a lowercase sigma. We've also done sigma this year with the kind of this thing over here. That's also sigma. Means the summation of terms in a sequence, but this sigma in this context means standard deviation for this set of data. Okay, it's all calculated from here. On your calculator, go to second vars. Okay, so go ahead and take a second to find where that vars button is. Vars is next to clear. It says distribution above it. So if you hit second vars, what we're doing is we're doing a normal CDF. And you can double check me on this, but I'm pretty sure CDF stands for cumulative distribution function. So we're trying to accumulate all the areas from my lower bound to my upper bound underneath this function, the normal curve. So go ahead and hit enter, and it's going to prompt you if you have an updated operating system. If you don't have an updated operating system, what you're going to do is you're going to put commas in between the values that you type in. So we know the lower bound is 37. Type in 37. If you don't have this screen, hit a comma right now, For the upper bound, we need 44. The mean is 39.7, and the standard deviation is 2.3. When you hit enter one more time, it's going to paste it. If you hit enter here onto the home screen, if you have a non-updated operating system, you probably had something that looked like this on your screen. Hit enter one more time, and it tells me that that is 0.849. Okay, so the area between those two values on the normal curve in this distribution would be 0.849. Okay. Of course, there's another way of doing it. So just to show you another path that we could take, we could actually type in the z-scores that we calculated. So the lower z-score was the negative 1.174. The higher z-score is 1.870. The mean for this is going to be at 0 as a z-score, right? That makes sense based on what we've seen for the normal curve. And what you're going to put for sigma is you're going to type in 1. And hopefully, you're going to get 0.849 if you do this all in terms of z-scores and not in terms of the actual values. Let's just kind of double check that real quick. Second bars, option 2, we want negative 1.174, 1.870, 0 for the mean, 1 for the standard deviation, paste it, hit enter, and I get 0.849. Now notice the 3 decimal places, those values are identical. If you go out a little bit further, because of the rounding we do with our z-scores, these are not going to be identical to one another. But notice how if I go out 3 decimal places with my z-scores, I get a fairly accurate representation of that area under the curve to 3 decimal places. So based on that, what do we now know? So round our probability to the nearest thousandth, which I already did. So 0.849 is the answer here. And what does that mean? Approximately 85% of the times will occur between 37 seconds and 44 seconds. Okay, so it's kind of introducing that probability aspect of based on what we know about normal distributions, we should expect these times to occur 85% of the time. Okay, let's do a few other cases with the swimming example here. Okay, so using the same mean and deviation from the last example, find the probability that this swimmer's time is more than 45 seconds. Okay, sketch the normal curve and shade accordingly. So in this one, we have the same normal curve here. We've got our mean at 39.7. The time is 45 seconds. And I want the probability, what are the chances that we're going to be out here? So we know that there's 2 ways to do it. You can do it with a z-score. You can do it with the actual numbers that we have here, the time that we're given. But to get a little bit more practice with z-scores, let's convert 45 to a z-score real quick. So z would equal 45 minus the average over the standard deviation of 2.3. So the z-score here is 2.304. And then using that information, we're going to calculate that area that we've shaded using normal CDF on the calculator. But there's one kind of catch to this. When we type in the lower and the upper bounds, we're starting at 45 seconds on our chart. But how do I tell the calculator that I want to go to the right forever and ever and ever and ever? So what we're going to enter, and I'll show you what the keystrokes are on the calculator, is you're going to type in something that looks like this, 1E99. And that's the calculator's scientific notation way of writing 1 times 10 to the 99th power. You can imagine that that's a tremendously large number, such that we're capturing a ton of area to the right that's infinitely getting smaller and smaller and smaller. So we can definitely still do this. We're essentially trying to type in infinity by choosing a huge number for the upper bounds. Okay, we know that the mean in this case is 39.7, and the standard deviation was 2.3. So let me show you how we can type in that 1 times 10 to the 99th here. Okay. So we're going to go to normal CDF again, second vars, choose option 2. We want the lower bound to be 45. For the upper bounds, type in 1. All right, to get the E, you're going to hit second comma. Okay, right above the comma, there's that double E there. So second comma would give you the E that we need for scientific notation. 1E99, 1 times 10 to the 99th, with a given average of 39.7. Here's the standard deviation. Okay, if I paste that, we've got 0.011 to the thousandths place, right? So we knew that this probably wouldn't be very likely, but you can see if I calculate this as a percent, that's going to happen about 1% of the time. Just as a quick aside here, you could have done this with your z-score of 2.304. Your upper bound would still be 1E99. And then just remember it's 0 and 1 for the keystrokes if you're using z-scores. Okay. Finally, what if I want to bound something below